quantum mechanics. We reviewed the classical formulation of classical mechanics based on Lagrange principle and Hamiltonian formulation. We did a very, very high level bird's eye view of molecules, bonds, atoms, and so on. So now we're going to start with dealing with the solids, with crystals, and see how we can proceed, first of all, by formulating the problem. So we have to write down the total Hamiltonian, that we need to write down the Schrödinger equation for this extremely large system. It's a lattice, so we have electrons, we have ions, they all move and interact together. So we'll have to write down the Hamiltonian. Having written it down, we'll have to stare at it and see what we can do to solve it, because it will be a daunting problem. So this will be what we'll discuss today and probably tomorrow. And then we'll go and see some simpler formulation of the problems, which can be used to calculate in relatively simple terms the excitation spectrum of a crystal. So, as I said, you can see in the slides and in material, the lecture notes that I've posted, a discussion about what we're going to deal with. It's a complicated many-body problem. We have many electrons, we have many ions. Many means a lot, 10 to the 22nd, 10 to the 23rd, depending on the size of the system that we're dealing with. Of course, we have a major help, which comes from periodicity. So what we're going to deal with is actually consider an infinite, uniform, homogeneous solid, periodicity, and the symmetries of the system, of the lattice, will come to help in simplifying the problem, but we will need many approximations. Besides knowing what the single electron wave function is, thanks to the periodicity, we can use Bloch's theorem, so the wave function of a single electron can be written in a simple way. We'll have to find out how we can formulate the problem in terms of single electrons, which is a major approximation. So that will be the task that we will have to face. Before going there, I'd like to go back to what I mentioned last time. We were talking about exchange energy. Where is it coming from? The fact that we have to anti-symmetrize the wave function of a many electron system. And I mentioned a possibility of looking at a simple problem, which is what I would like to discuss. I decided that perhaps it's better to look at it in detail, explicitly, to see what we will find in solids, more complicated situation, but the physics is the same. So the idea is, let's consider a particle in a box. So we have a potential which is flat. Let's set it equal to 0 between 0 and L. Think about a quantum well with L, the typical classical, not classical, but quantum mechanical problem where a particle in a box that you see in introductory quantum mechanics, infinite walls. So the potential is infinitely high, which means that the wave function has to be 0 at x equals 0 and x equal L. And so the wave functions have this form, which actually is normalized already, so that the integral between 0 and L of the square of the wave function is equal to 1. Now, the idea is, okay, that's for one particle. What if I have two electrons? Let's assume that these electrons, let's ignore spin, so let's make things simpler. And let's assume that these two, let's call electron particles for now, in general, that these two particles can satisfy different statistics. So they can either occupy the same level or not, but let's assume that they do not. So let's consider one particle in the ground state of the system, the other particle in the first excited state. So let's call n equals 1 the ground state, n equals 2 the first excited state. Let's look at their wave function, so the two particle wave functions, in three different situations. One, the particles are distinguishable, which means the wave function will be just the product, the wave function of the two particles will be just the product of the wave functions of the two particles separately. The second case will be the assumption that the electrons actually, or these particles, obey Bose-Einstein statistics, which means that the wave function has to be symmetric under permutation of particle 1 with particle 2. And the third case will be the case of fermions, particles which have high integer spin, and the wave function has to be antisymmetrized. As I said, I'm ignoring spin now, I'm putting spin back, but the idea is where the particles obey classical statistics, they're distinguishable, or the particles obey Bose-Einstein statistics, which is what half-integer integer spin particles do, or they're fermions, so half-integer particles, and they obey the Fermi-Dirac statistics. And the idea is to look at a wave function and calculate the expectation value of the mean square separation of the particles. So we want to look essentially at the root mean square, RMS, distance between the two particles. X1 is the coordinate of particle 1, X2 is the coordinate of particle 2. Particle 1 sits in a ground state of the system, so its wave function is described by this expression with n equals 1. The second particle is the same expression, but n equals 2. And we calculate this expression. So, and calculate the expression means we look at the expectation value. So what we do is we take the square of the distance between the two particles, and we average it by integrating over x1 and x2, the coordinate of particle 1 and particle 2, multiplied by the wave functions, okay? This in the case in which the particles are distinguishable, which is a situation that you would have for classical objects, classical particles. It's a little bit laborious in terms of algebra. It's trivial, as they say in papers, it's straightforward but tedious algebra. You have to expand the square, and then of course you have to integrate over x1 and x2. At the end, if you follow the algebra, I'm not going to go into details, but if you follow the algebra, you find that the mean square separation of the two particles considered to be distinguishable, so they obey classical statistics, Boltzmann statistics, so to speak. The mean separation, the mean square separation, is about 1/10 of the L squared, the square width of the well. And if you take the square root of this object, you find that roughly the two particles are separated by 1/3 of the width of the quantum well. And so that's a classical result. What we're going to do at the end is to say, well, suppose that these particles are charged. Then clearly there will be some Coulomb repulsion between the two. How strong is this Coulomb repulsion? Clearly, the closer the particles are, the stronger will be the Coulomb repulsion. So we'll discuss a little bit about cell consistency at the end, and that will be actually the rule of the game when we'll deal with solids. So first case, electrons are classical particles, so these objects are classical objects, and their mean separation is about 1/3 of the width of the well. This is a particular case in which one particle is in the ground state, the other one is the first excited state. Good. What if the particles instead now are indistinguishable, but they obey Bose-Einstein statistics, which means their wave function now has to be the symmetrized wave function. So what you see here is I take the product of particle 1 and particle 2, and then I simply swap the n and m, the indices. So this is the wave function of particle 1 in a ground state and particle 2 in a first excited state. And this is the opposite, particle 1 in a first excited state, particle 2 in a ground state. And then I do exactly the same calculation. So I calculate the root mean square separation of the two particles by doing the same integral. This becomes even more laborious. I have two terms now. This is essentially what we had in the first slide, the first case. But then we have an additional case and then the cross terms of the square of the wave function. So lots of integrals. Again, straightforward but tedious. At the end, if you work out all of the algebra, and here I give some details, you find out that the separation of the two particles is about 2/10, 1/5 of the length of the well. So notice this was 1/3, this is 1/5 now. So if the particles are bosons, so their wave function is symmetrized, the particles tend to be closer together. They stick together closely. Therefore, their Coulomb repulsion, if these particles were charged, which is something that we're not considering yet, then their Coulomb repulsion will be stronger. Let's consider the third case. Now, the particles are distinguishable, again, so they're quantum particles, but now they obey Fermi-Dirac statistics. So their wave function has to be antisymmetrized. This is exactly the same thing that we saw before for bosons, except that now I had a minus sign. And this will imply that the algebra will be exactly the same algebra that followed here, but the cross term will have a minus sign. So there will be a reduction in the distance between the, an increase of the distance between the two particles, okay? So I follow the same algebra that I followed before, and now the result is that the mean root mean square separation of the two particles, again, the expectation value of x1 minus x2 squared, is 2/5. Notice that this is twice as big, roughly, twice as big as the separation that I have when the particles are bosons. They obey Bose-Einstein statistics, and it's a little bit bigger than the separation that you have when the particles are classical, say obey Boltzmann statistics. So again, this is nothing to do with the energy. We're simply, for now, we're simply considering what is the mean separation of these two particles. Now the idea is, what if these particles are electrons? So I'm leading into what we will have to get into when we'll deal with solids. If the particles are charged, of course there must be some background positive charge, call it a Gellium model so that the system does not explode, and that will be the ionic charge in a crystal, of course. But the electron charge now has to be taken into account to calculate the energy, and we see that the energy is reduced when the particles obey Fermi-Dirac statistics, because they tend to be separated more than what you would have if the particles were either distinguishable, as in classical physics, or they obeyed Bose-Einstein statistics, so if they had integer spin. So that will be the first effect. There's more, and that's what we'll have to go into. There's more because we have not assumed anything about the potential. We have kept it fixed as a flat potential in the well. Clearly, if these particles are charged, now the potential will have to change. So we'll have to calculate the energy, the charge density corresponding to the particles that we have, solve Poisson equation, ignoring retardation effects. So I'm not going to talk about Maxwell's equation. Poisson will suffice. So we'll have to look at the potential charge due to the presence of these particles, solve Poisson equation. Of course, this changes the potential, so this will change the shape of the wave functions because we will have to solve Schrödinger equation again. And there are several approximations that we will have to invoke dealing with crystals. The first one is the obvious one, which is called the Hartree approximation of the mean field or self-consistent field, whatever you want to call it. Essentially, we'll calculate the charge by just squaring the wave functions of the two particles and multiplying by the electron charge, divide by the area, normalization area. We'll get some charge density, solve Poisson equation, plug the potential back into Schrödinger's equation, and this will give us the new solution for the wave function, and eventually we keep iterating. So with this iteration process, we'll get eventually to convergence. That will be okay, except that we're ignoring the fact that the wave function has to be antisymmetrized. So the better thing would be, after we compute the wave functions, we antisymmetrize it, we calculate the charge in this new situation, and we proceed that way. That is something that we will call the Hartree-Fock approximation, which is an improvement of the Hartree approximation, because we account for spin somehow, for this antisymmetrization of the wave function. And here, so far, I've always said, let's say at the beginning actually here, that the functions are the wave function of the electrons is just the product of the two wave functions of single electrons. Well, that's not necessarily true. In principle, I would have to solve the problem exactly. And this is what we call the correlation energy. I told you that the most realistic and more accurate or fair definition of correlation energy is the difference between the exact result and what I can calculate. Essentially, it's if you want, is a pragmatical definition. The electrons actually will redistribute themselves in a slightly different way if you allow them to take a wave function which is not just a factorization of two single particle wave functions. Okay. Any question? Again, please feel free to interrupt me anytime. I realize that there's not much of an interaction from you. Maybe it's a cultural issue. I'm used to have being interrupted quite often. So please do, whenever I say something that is not clear, whenever you wish me to go in detail into something that I just gloss over quickly, please let me know, and if I'm able to answer, I'll answer. If I don't know it, I don't know it, and that's it. Okay, so let's get back to our main track of what we wanted to discuss. So we have to talk about the crystal Hamiltonian. So that's a big problem, right? We have to write down a Schrödinger equation for a system that has many ions, many electrons. Notation-wise, the little r's with the little subscript I, they will be the electron coordinates. I will run between 1 and the number of electrons that we have in the system. If the system is normalized to a finite volume, this will be a finite number. Large, very large. Big R, with a little subscript alpha, those are the coordinates of the ions. So remember, we have many cells. This big R can be written as the sum of the coordinate of a cell, the position of a cell, so a lattice point. Remember that the crystal is the sum of a lattice and the basis. So this big R will be the sum of the lattice points, which are defined in terms of the primitive translation vectors of the solid. And then, of course, there will be the coordinate of the ion referred to the origin of each cell, the basis, if you wish. I have to be a little bit careful about the notation here because we have so many indices and subscripts, superscripts that it can get confusing. So let's write down just the classical Hamiltonian of the system. Eventually we'll have to quantize it. We will not deal with second quantization yet, so we'll treat it as a classical, sorry, not a classic, a conventional quantum mechanical problem, except that it's very large. So it's conventional, but extremely hard to solve. Impossible, actually. So what do we have? First, we have the electrons, and we have to write down the Hamiltonian for all of the electrons. So we sum over all the electrons their kinetic energy. P is the canonically conjugated momentum to the coordinate of little r. This is little p. Is just the gradient, okay, the nabla square, so the Laplacian if we take the square of this object. So this is the usual kinetic energy of all electrons. All electrons, fortunately, have the same mass. Then we have the Coulomb interaction, which is repulsive among all of the electrons. So I'm using SI units here, so it's just the Coulomb potential between two electrons at two position R and J. The sum over I and J, of course, we will mean whenever we sum over electrons, we will imply that I cannot be equals to J. The electron doesn't feel itself electrostatically. And then there is a 1/2 here because I have to make sure that I do not double count the interactions between the pairs. If electron 17 interacts with electron 45, I have to take it only once, not when I swap the 45 and 17, right? So there is the 1/2. Sometimes I will put a prime to the summation symbol, implying that without the 1/2, implying that this is understood, that I'm not double counting and I'm not counting each electron I itself. Then we have to do the same thing for the ions. The ions do the same thing. This is repulsive, remember. For the ions, it will be different. This will be attractive, so this U will be negative. We have the kinetic energy of the ions. So it's the square big P, which is the momentum canonically conjugated to their coordinates, or position big R. The mass in principle changes. Clearly, the mass may vary between ions in a single cell, but then it's the same in every cell. I'll lump all these indices about cells and ionic position in each cell into single index alpha. Then there will be the same story. The ions interact among themselves. Actually, this will be a binding energy. This is a complicated potential, extremely complicated, because it will not be just the repulsion between the ions, clearly. The ions actually bond. There are chemical bonds which are formed. The reason why this is attractive is that we have the electron cloud which enters this U. So you begin to understand how complicated the system is. The problem is extremely complicated because this U will depend on the electron distribution, the bonds. Or if it is, say, a metal, it would be a metallic bond. It would be the cloud of electrons which are distributed uniformly in the metal. If it's covalent, it will be just the electron density in the orbitals which constitute the bond. If it is ionic, it will be the charge distribution between the ions. And eventually, these electrons interact with the ions. So there will be some electron-ion turn, which is actually what puts the electrons in the crystal and make them bind to the ions. So this is an extremely complicated problem. We have a Hamiltonian, which if we plug it into the Schrödinger equation for the system, we have, first of all, we have a wave function that depends on all the coordinates of the electrons, all the coordinates of the ions. They're all free to move. We have to write a Schrödinger equation for this many degrees of freedom, all the electrons' degrees of freedom, 3 times the number of electrons, 3 times the number of the ions. So we have a huge number of variables. The problem is daunting because it's even nonlinear if we write a Schrödinger equation this way, because this U captures the electron distribution and this V as well, the interaction between the electrons and the ions. An electron in an outer shell, say in an upper valence band, will have to feel also the potential which is screened by the core electrons in the ion. So it's a daunting problem. So it will be a little bit culturally challenging, I think, here to see how we will simplify the problem. And that's what we're going to do in the next step. So it's an extremely complicated problem. What saves us? The periodicity, clearly. The fact that this crystal is periodic will be a huge simplification, because essentially we'll be able to map the Hamiltonian for an infinitely large system, okay, or very large if you use finite volume normalization, to essentially studying what happens in a single cell. So there will be a huge simplification thanks to Bloch's theorem and other things. But before we get there, we have to go and make several approximations. Just to make sure, am I online? Can you hear me? Do you still see the slides? Just occasionally, I want to make sure that I'm okay here. Can you hear me?
Yes, Professor, we can hear you, yeah.
Good, okay. Yeah, as I
Yes,
said many
Professor.
times. Good. So I'm not talking to myself. So the problem is unsolvable. So we need some approximation. So the first, I'm listing here approximation. We'll discuss them in more detail shortly. The first approximation that we're going to make is the so-called adiabatic approximation, or Born-Oppenheimer approximation. The idea is that the electrons and the ions, let's go back here, have very different masses. Even if we consider a light crystal like, I don't know, graphene, which is popular nowadays, is a two-dimensional material. Even carbon, yeah, it is light in terms of ions, but it's still much, much heavier than electrons, right? So it's something like 10,000 or more times heavier than an electron. So we have several orders of magnitude difference between this mass, or the masses of the ions, and the electron mass, which means that if we look at how they move in time, the electrons will wiggle and jiggle extremely fast compared to the slurry, slow motion of the ions, because they're heavier, so their inertia is much higher. So we may think in terms of looking from an ion, from the perspective of an ion, the electrons look like a cloud. The fact that they move in time is kind of irrelevant. They move so fast that they fill their orbital, so to speak, in a steady state fashion. Vice versa, for an electron which is moving around an ion, the ion moves so slowly that in practice we can solve the problem of Schrödinger equation for the electrons by treating the coordinates of the ions as parameters. They move so slowly that every time an ion moves a little bit, the electrons adjust instantly, adiabatically. So that would be the first approximation. This will permit us to split the total Hamiltonian that I've written here into two pieces. if we consider this as a parameter here, you see that we have a first term which is just an electron Hamiltonian, and then an ionic Hamiltonian, where this U now contains some sort of steady state time average of the electron distribution. So we'll decouple the problem. Clearly, there will be situations of extremely relevant to what we deal in this class, in which we'll have to go a little bit beyond, and then we'll use perturbation theory. So if you want to deal with the electron ion Hamiltonian when the ions move a little bit away from equilibrium, phonons, when their motion is quantized, this will give rise to phonons, then we'll have to deal with electron-phonon interaction. But we'll deal perturbatively with this effect. As a starting point, in order to compute the band structure of a solid and even their vibrational spectrum, so to solve the ionic Hamiltonian, we will decouple the two. Okay, big simplification, but not enough. We're still stuck. Now, if we consider only the ionic Hamiltonian, the little L here stands for lattice. So the lattice Hamiltonian and the electron Hamiltonian, they're still very large Hamiltonians. By large, I mean they deal with wave functions or with a system with a large number of degrees of freedom. So we'll need some simplifications. So dealing with the lattice Hamiltonian later, and in class we'll deal with it at the appropriate time when we'll start dealing with elementary excitations on solids and how to quantize them. The first thing we'll do is to go back to what we were discussing before, dealing with the simple problem of two electrons in a box. We'll go to a single electron approximation and use the same self-consistent field idea. Each electron, consider one electron in particular, that electron will fill the average field of all of the other electrons. And that will lead us to the Hartree approximation. We can improve it by considering the fact that the wave functions have to be anti-symmetrized. Now the anti-symmetrization is not an easy thing to do because we have so many electrons, we have to look for a wave function which has to swap sign whenever we swap the two electrons, each pair independently. And this will lead us to a formulation of the wave function which is called the Slater determinant of the wave function. We will discuss it in a moment. Not enough. Well, we can get some ideas, some general ideas about what the excitation spectrum of the solid would look like. Excitation spectrum means the conduction bands and valence band as well, but so how the band structure looks like. But there will be a big issue. And the big issue is the exchange energy, which is somehow taken into account by the Hartree-Fock approximation, but actually we cannot do the Hartree-Fock approximation exactly in a crystal. It's too complicated. Even if it's an approximation, it's just unworkable. There are some recent progress leads to some formulations which do it a little bit better than what we will discuss in class. But we'll have to deal with the big problem on how to deal with the exchange energy, since we cannot do the Hartree-Fock exactly, how to deal with it in an appropriate way, and particular correlation, which is, my understanding, is still an open problem. I mean, we know how to do it correctly, but again, it's unworkable from a computational point of view. And so we will introduce what is the main assumption that we will deal with in the rest of the class, which is density functional theory, and actually we'll deal with even simpler version of empirical version of this theory. So this is just the outline of what we're going to discuss. So the first approximation is this, the Born-Oppenheimer or adiabatic approximation. So what we do is, from the considerations that I discussed before, the fact that the ions move much more slowly than the electrons, we essentially think of the total wave function. It's kind of hard to find Greek letters, uppercase Greek letters for wave functions. So I call this big Greek letter xi. This is the total wave function, which is a function of all of the ionic coordinates. By R, I mean here the collection of all of the coordinates of the ions. Little r is the collection of all of the coordinates of all of the electrons. So this is a a huge number of variables. This is the total exact wave function of the crystals. No way we can get it. So the first step is to split it, to factor it into something that depends only on ionic coordinates, and this will give us a way to deal with the vibrational properties of the lattice, how these ions vibrate in a perturbative way, and the electronic part. Notice that the electronic part has a little subscript r, which is the coordinates of the ions. Again, as I said before, we'll treat it as a parameter. So we will consider the electrons as responding instantaneously, adiabatically, to every possible displacement that the ions might have. And calculated the band structure, we will fix actually these coordinates at their equilibrium position, calculate it somehow, determine experimentally, whatever we find it appropriate to do, and then we will solve the Schrödinger equation for these electrons, all of them, treating this as fixed. Okay, so this is the major advantage of the adiabatic approximation. By the way, I didn't write it here. It usually works very well. In most cases that one can encounter, it works extremely well. In metals, you have around the Fermi level so many electrons that can respond instantaneously when I move an ion. So screening, if you wish, is so quick that this is a very, very good approximation. In dielectrics that have a band gap, electrons don't move across the gap. They may rearrange in the valence bands, but they cannot cross the gap when they displace the ion a little bit. So again, this approximation is very good. The only case that I can think of in which this fails, not dramatically, but there are some symptoms that the Born-Oppenheimer approximation fails, is actually in graphene. Graphene is neither a dielectric nor a metal. It doesn't have a gap, but the density of states at the Fermi level is 0. So it's sort of a frustrated metal. It would like to be a metal, but it cannot, because at the Dirac point, the density of electronic states is 0. So actually, electrons do respond a little bit sluggish to displacement of the ions, even small displacement, because there's no gap. So they can acquire an arbitrary small amount of energy, and there is a delay in how they respond. There are not that many, so they don't screen instantaneously. And indeed, as I said, there are some hints that the Born-Oppenheimer approximation doesn't work terribly well. It works roughly, but not terribly well. And this is related also, it's the same argument, why some approximations to treat dielectric screening, the so-called random phase approximation, doesn't work either. So graphene is a pathological case. All these Dirac materials are a pathological case. But in all the other cases, metals and dielectrics, which is the rest of the solids we'll consider, the approximation worked very well. So I wrote it here equivalently in time, looking at the time-dependent Schrödinger equation and wave functions. So we write the wave function that depends on the ionic and the electronic coordinates. It's a function of time, and we split it into two parts, two factors, and one is just the ionic component, and the other one is the electronic component, where again, this is treated as a parameter. You can have some hand-waving arguments or more rigorous arguments where which justifies this. You can actually write formally the Schrödinger equation by splitting the lattice Hamiltonian, the Hamiltonian into a lattice component and an electronic component, and then the electron-ion interaction. You can formally derive and see that the error that you're making, which is essentially the sandwich between the lattice Hamiltonian of the electronic and the lattice component, is roughly or the order of the ratio of the masses smaller than the terms that the lattice Hamiltonian and the electron Hamiltonian themselves. So when the ionic mass is 4 orders of magnitude or more bigger than the electronic mass, then you see that you're making an error which is 0.001%. So extremely good approximation, with the caveats that I told you about graphene. I keep talking about graphene because it's of interest today, and There have been several interesting papers showing the limitations of the Born-Oppenheimer approximation, which usually one doesn't worry about because it works so well. Any questions so far? Everything clear? Okay. So we separated the, where am I here? We separated this big Hamiltonian into this piece, the central piece, this object here, which is a lattice Hamiltonian. This U includes the electron density, but we'll assume that electron density is the ground state electron density of the system, and we can treat this separately from the rest, which is the first two terms and the last one, where here now the R sub alpha will be frozen at equilibrium position, so that the electronic Hamiltonian does not depend on the ionic motion, because we keep them frozen thanks to the adiabatic approximation. The ionic Hamiltonian, the lattice Hamiltonian, is something that we can discuss briefly, but we'll talk about it later on. The typical idea, we'll deal with it actually in great detail. We will have to introduce phonons and all these things, but just to give an idea of how we're going to handle this lattice Hamiltonian. Remember, the lattice Hamiltonian is the kinetic energy plus the potential energy. And the potential energy was the sum for each ion alpha, was the sum over all the position of the ions beta, all of the other ions, of their potential energy. What we do is essentially we expand around the equilibrium position. So we do some linear response or perturbation theory, whatever you want to call it. So we expand into Taylor series, if you wish, the potential around the equilibrium position of the two ions. So at first we consider the first term, the term in which this distance between the two ions is the equilibrium distance. Then in principle we have the first derivatives of the Taylor expansion, right? Well, actually if you sum over all of the ions, the gradient, this will be the first term, right? The gradient of the potential energy between the ions, well, the gradient is just the minus the force acting on the ion alpha. And we sum over the forces due to all of the other ions beta. But if we expand around equilibrium, at equilibrium, the sum of the forces acting on ion alpha due to all of the other ions beta has to be equal to 0. Otherwise, it wouldn't be an equilibrium at all. If you wish, we're at the minimum of the potential energy, and we take the first derivative at the minimum. It is 0 by definition, because it's an extreme point. So the first, the leading term in our expansion will be the term which contains the second derivatives with respect to x, y, and z of the coordinates of the ion beta, of the difference between the two, multiplied by the displacement of the ions, okay? This is what's called the harmonic approximation. Of course, there will be other terms. That's why there is the double swiggle here that I'm ignoring, the so-called anharmonic terms. And you see that immediately that we get the simplifications, because the Hamiltonian that we have now, particularly if we diagonalize this object, which is the second derivative, so the potential energy, this is called the dynamic matrix. If we diagonalize it, essentially we can decouple all the modes and we get a collection of Hamiltonians of harmonic oscillators that depends on the square of the momentum and the square of the position. And then we can treat it as harmonic oscillators, and that's what we will do in the future. And actually, we will see that when we'll deal with second quantization, the task will be always to formulate the total Hamiltonian of the system as a sum of Hamiltonians which will have the form of the Hamiltonian of harmonic oscillators, and that will be the building block of our many-body theory. Okay, so we'll leave that for later. We will explain first for the simple case of a one-dimensional, a linear chain of ions, monatomic or diatomic, and we'll see what the eigenmodes of the system are, the eigenfrequencies and displacements. So we will deal it in detail. But for now, let's leave it alone. Let's just keep in mind that we will have to deal with it somehow. Of course, using Born-Oppenheimer approximation and concentrating our attention only to the electron Hamiltonian, we leave the electron-ion interaction away from equilibrium that we will have to deal with it later, again, by using perturbation theory. And also, as I talk here, there will be other terms here. They are mainly, they call anharmonic interactions, anharmonic terms. They actually physically reflect the fact that phonons can decay. They can interact among themselves. And so we will not deal with it, but in principle, particularly for people who are interested in thermal transport, this is a big issue in today's VLSI or ULSI technology because of the heating of devices and treating transport of heat away from a device is a very complicated term, and you have to consider also the decay of, say, optical phonons into acoustic phonons and so on. And this is represented by the terms that I haven't written down here that we're ignoring here. So keep that in mind, that we're ignoring terms which are very important for some applications like thermal transport. All right. Any questions so far? Good. So we're left with let's call it simpler in big quotation marks, because it's not that simple at all, but at least now we do not have the ionic motion interfering with our calculations. The ions are here, poof, they're frozen at their equilibrium position. We're not going to bother with them for now. As I said already, we'll deal with it later when this thing moves a little bit away from the equilibrium position, but for now we will ignore it. It's still a huge problem. We still have a wave function, which is the wave function of big N sub-electron, big number of electrons. Of course, can be huge. We have to simplify it. So the first idea is, let's do the simplest thing that we can think of. Let's suppose that this wave function is the product of single particle wave functions. So I have various eigenstates of my system, of the electrons around the ions, and I consider the total wave function as the product of single electron states. And then what I'm going to do is to consider the mean field that each electron feels. So I will lump, this is the troublesome term, right? It's the Coulomb interaction about the electrons. And this one as well, because it's the interaction with the electron, with the ions, and you realize that this is an attractive term, this is a repulsive term, which screens dielectrically the electron-ion interaction, so it gets messy. On top of everything, and this is what I discuss here, we have to consider the fact that it's complicated if we have to anti-symmetrize this wave function. So whenever we swap the indices of two electrons, this big function, big psi wave function has to change sign. So let's ignore it first. So let's consider first the self-consistent field, single electron approximation. And so let's lump the effect of all of the other electrons. By this I mean the electrostatic potential of all of the other electrons. And I say electrostatic because I consider a time average of it. So just a solution of Poisson equation where I take the wave functions, time independent, stationary states, I add them all up, multiply by the electron charge, solve Poisson equation by adding, of course, the attractive potential of the ions, the nuclei, and then I'll look what I get. So what will we do is we come out with an expression. You see, I have the kinetic energy of the electrons now. I have the lattice potential, which includes also the screening of the electrons. And then I have this Coulomb repulsion. This is negative. It's an attractive potential. Otherwise, the crystal will not stay together, will disintegrate. And this is a repulsive interaction. What you can do is take the, this is the square of electron, the wave function of electron J. I multiply by the charge. I get the charge due to the electron J. I integrate, this is just the Green's function of the Poisson equation. So I calculate the potential due to each electron J, a sum over all of the electron J. By the way, I could add a 1/2 in here, not to count twice the same electron. Okay, this is implicit in this sum. And this gives me the potential due to the charge of the other electrons that I calculate by calculating the square of their wave function. So I start with some guess. If I want to calculate it, start with some guess for what the potential looks like. I calculate the wave functions of all of the electrons. I look at where the electrons have to go. I populate the states that are occupied at equilibrium. Given the density, I can calculate the Fermi level of that electron distribution and see which states are occupied. I calculate the charge. I solve Poisson equation by adding the charge density due to the other electrons. I add the ionic potential. This gives me new potential. I solve Schrödinger equation. I get some wave functions for each electron, and then I can iterate. This is the Hartree approximation. Let me know if it is not clear. Two considerations. The lattice potential is a periodic function, of course. Even if this doesn't seem to be periodic, it is, because this is the square of a wave function. Remember that the square of a wave function is periodic. The wave function itself does not have to be periodic. There is the phase, e to the a chi r, okay, which is the Bloch's theorem. But the square is periodic. So this is a periodic potential overall. So I can use the periodicity to simplify the problem. We will deal with this in later. The second consideration is a tricky thing. This looks very much like a Schrödinger equation. I have a Hamiltonian acting on a wave function, which is a single electron wave function. Remember, I expressed the total wave function as a product of this single electron wave function. And this seems to be an eigenvalue. This is a tricky issue. This is not the energy of the electron. Let me see how we can make it clear. We have a system of interacting particles. If you consider a system of 10 particles, and they're not interacting, they're neutral. So there's no Coulomb interaction among themselves. And they're distributed among various energy levels. If I remove one particle, clearly the total energy of the system changes simply because I removed the energy of that particle. Good. If I have a system of particles which are interacting, things are not so simple, because I have these many electrons, they occupy all these energy levels, and then I remove one electron. The energy of the system changes in two ways now. One, I have removed the energy of an electron. But two, and more important and more complicated, I've changed the charge distribution of the system now. There is an electron, one fewer electron in the system. So the total energy of the other particles which are interacting among themselves now changes, because the screening effect of that electron is gone. Could be attractive if it has to screen the ionic interaction, could be repulsive, it is the Coulomb repulsion among the electrons. But now you see that this is not the energy of an electron. Actually, there is a theorem called the Koopman theorem that says that this is actually the ionization energy. So it is actually the energy that it's required to take an electron out of your electronic system. The ionization energy, and bring it up to the vacuum level. To put it in another way, if you solve this equation iteratively, self-consistently, right, the way I said. So this is the Hamiltonian. It's a nonlinear Hamiltonian, a nonlinear Schrödinger equation now, because this interaction terms contains the unknown itself. So it's an integral differential equation. But you can solve it iteratively, as I said. Start with a guess, finding the variable size, plugging them back in the first iteration to calculate this term, using the wave functions you calculated at the previous iteration. You find new wave functions, you plug them back in, blah, 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 you keep iterating until hopefully you converge. Good. Then you get these values, let's call them eigenvalues in quotes, these energies. You realize that if I add the energies of all of the electrons, this is not going to give me the total energy of the system, because it will double count the interaction among all of the electrons. So this is a distinction that we have to be aware of. When we'll deal with pseudopotentials and density functional theory, things will get even more complicated, because the parameter that enters here that one calls the single state energy, or the eigenvalue of the Hamiltonian, actually has a physical interpretation which is extremely doubtful, extremely obscure, I say. In addition to this consideration, there is the fact that we live we'll consider pseudo potentials, pseudo wave functions, and we'll describe what they are, which are not the real things. So it will be a little tricky, and keep that in mind. I will slip into the same problem and say, this is the eigenvalue, is the energy of the electron. Keep that in mind, okay? And despite what I may say, as Feynman once said, try and understand to what I mean, not to what I say. So, okay. So this is the Hartree approximation. We have this system, the Hartree equations, and then what Hartree did to find this problem, rather than doing it iteratively, which is what people usually do today, and you can do it with a Hartree-Fock method for a few electron systems. What he did actually was to use a variational argument. Let's calculate the expectation value of this total Hamiltonian. The H here, sorry for the double H, this stands for Hartree now. So it's this, oops, okay, where am I? I lost my slide, here we go. We calculate the expectation value on a wave function. We parameterize this wave function, and then we look for a set of parameters that minimizes this expectation value, the energy, and this is just a normalization factor. And if you find out that actually what you find is that the total energy of the system, which is related to what I said, is the total energy that you can obtain by adding up these things, but then you have to subtract this term, okay? Which is the fact that I was saying. There is a 1/2 here, you're double counting the repulsion among all of the electrons. Actually, it's between 2 electrons in each pair. Okay, what am I missing here? What we're missing is spin. We're missing the fact that electrons cannot occupy the same state, characterized by exactly the same set of quantum numbers. We're missing the fact that the wave function has to be anti-symmetrized when the electrons have a symmetric part of the spin, symmetric spin part of the wave function. So the suggestion is to do this. How can I express the total wave function of my electronic system in terms of single particle wave functions? So as we did here, as a product of a single particle wave function, but with the characteristics that if I swap 2 indices, if I swap 2 indices, I flip the sign of the wave function, which is what the fact that electrons are fermions implies. The idea is to use what's called a Slater determinant. So I take, if you want, this is just the wave function of 1 electron. Let's call it psi1, and this labels the electron index. So what I do is I build a determinant in which I have the wave function psi1, but in each row, in each column, if you wish, this wave function is populated by a different electron. So I build psi1 for R1, psi1 or R2, blah, 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 all the way to psi1 or N. And here I do the opposite. I look at all the possible wave functions that I have in the system, 1 electron wave functions, always with R1. And then I build a determinant. You see immediately by the property of the determinants, you remember how to calculate determinants of a matrix, it's a plus, minus, plus, minus. Whenever I swap 2 indices, 1 with 2, I gain a minus sign. Because it's equivalent to going from this term to this term, from a plus to a minus. Can I do this in a crystal? No way. This is a problem. Remember that this is normalized by the factorial of the number of electrons that I have. Sorry for my clock, 10 o'clock. Let's my German chime and good, okay? So the size of the determinant is huge. It's the factorial of the number of electrons, so no way. The best I've seen is, I think people studying quantum dots, they dealt explicitly with a Slater determinant of something like 6 of electrons, maybe more, 6 would be what, 720, something like that. So it's a huge numerical enterprise here. So it's not something that you can do. You can do in small molecules when the number of orbitals and electrons is not too big, but otherwise you cannot do it. So the alternative is to use this principle now. Here we used it just to show that this number, this parameter W sub I, actually is not what you would call the eigenstate of this Hamiltonian. It's a different object physically. It's the ionization energy by Koopman theorem. But what we do now is to plug this wave function, which now is a Slater determinant, and find what is the form of this Slater determinant of an equation that these single electron wave functions have to obey. Sorry, in order to minimize this energy. This is what Fock did, and the result is this. It's quite interesting. So this is a complicated process which requires the minimization of the expectation value of the total energy, assuming a wave function of this form. Again, remember that this is an assumption. Just to remind you, we already used the adiabatic approximation. We have decoupled the electron Hamiltonian for the ion Hamiltonian. We have now assumed a single electron expression so that the wave function can be expressed as, even in this complicated fashion, as a product of single electron wave function. So we already made lots of approximation, and still we are nowhere close to a form that we can solve in practice. So we'll have to do some more work. So the equation that these wave functions have to obey when the total wave function of the system is approximated by this equation, this Slater determinant, is the same form that we had before. Notice that this is exactly this. It's exactly the same as the Hartree Hamiltonian. There is the kinetic energy of each electron. I'm considering just one. There's the lattice Hamiltonian, the ionic Hamiltonian, attractive. There is the repulsion due to the other electrons. So I'm summing over all of the electrons, with a 1/2, of course, in front, their charge, E times I squared, and then just finding the potential via the Poisson-Green's function, which is due to this charge density. This is the Hartree potential. The Hartree potential does what? Do you remember from the first example that I had of two particles in a box? If I look at particles and I consider them classical objects, by classical object I mean classical statistics, Boltzmann statistics, their mean separation will be smaller than the separation that I have when the particles are fermions. Remember that we had 1/3 versus 2/5. It's not a big difference. You know, it's a little bit smaller separation when particles are distinguishable. So here, what we had another term. Notice that this term is exactly the same, except for the fact that I've taken the I and the J here and swapped them. So this now becomes, so the J here, which used to be outside the integral, so inside the integral, now has moved outside, and here I have the unknown wave function psi sub I, which enters, oh boy, sorry about that, okay, I lost my pointer. Okay, so here I have swapped the indices I and J. So I've converted what used to be already an integral differential equation, but at least if I wanted to proceed by iterations, it was clear what to do, because this does not contain the unknown yet. Here, the unknown comes inside the integral, so it really becomes a very nonlinear, messy integral differential equation. So it's a complicated beast. Again, this is the Hartree-Fock problem, and you see that this amounts to saying this is the Coulomb repulsion if the wave functions were neither symmetrized nor anti-symmetrized, the usual mean field for classical statistics. But now I reduce the repulsion because electrons in an anti-symmetrized wave function tend to stay as far away as they can, simply because of this exchange property. So this is the exchange energy, how to account for it. It's a reduction of the repulsion, exactly as we saw for the two particles in a box. So formally, I hope that it is clear what the procedure is. What is this equation? Again, what this W sub I is, it's a complicated story, Copeland theorem. This is actually the ionization energy. It's the energy that it's required to take electron I out of the system and bring it into vacuum. The problem, as you see, is if I have few electrons, I have a chance of solving somehow this problem. If I have as many electrons as I have in a crystal, there's no way I can solve this problem. Any question? Here's just some discussion of what I just said before. So this is the exchange term which reduces the total energy of the system. Okay, so this is what we're dealing with. I remind you, adiabatic approximation first. We're dealing now only with the electronic part of the Hamiltonian because we're considering the ions to be at their equilibrium position, and that's okay because electrons are assumed to respond instantaneously to every motion of the ions, which are so heavier and so much more sluggish. And this is the best we have could come up with, assuming a single electron picture. That's an assumption. In this case, we have obtained an equation which tells us what the single electron wave functions have to be, accounting for the fact that the total electronic part of the wave function has to be antisymmetric under exchange of any two indices of the electrons. How do I calculate this in a crystal? And that's where things get complicated. So let me rewrite this equation. This is kinetic energy, lattice potential, and then something which is a functional of the electron wave function. Okay? Excuse me. So this is a functional of the wave function, not of the density. However, there is, let's see, I have it here. There are some important theorems which simplify the problem. Remind you again, this is a functional of the wave function themselves, not of the density. Is it true in general? Fortunately, not. There is a couple of theorems which you can lump into a single one, the Hohenberg-Kohn theorems. They say that if I look at an electronic system, the ground state properties of the system, I should have highlighted this in red or in italic or something. The ground state properties of this system are determined uniquely and completely by the charge density of the electrons. So in principle, this functional, which could be a function of the wave functions, which is more complicated because the wave functions are not periodic, because there is a phase. Okay, fortunately, if I'm dealing with the ground state property of the system, this complication doesn't appear. The charge itself, density is sufficient. I don't have to worry about the phases of each wave function. So this is a major help, a major simplification. And this is at the basis of density functional theory, because we know that this entire mess can be rewritten in terms of a functional, not of the wave function, as I had in the previous slide, but as a function of the charge density. Okay, so all of the possible interference effects of the wave function, which is what is expressed by their phases, they don't matter. Okay, and so I can ignore them. The important caveat is that this is true only for the ground state. Why does it matter? Well, if I want to calculate transport in silicon, I have to know what the conduction band of silicon is. And conduction states are excited states. They're not ground states. So the valence band is good. I can deal with it. The conduction band, in principle, this theorem doesn't tell me that the conduction band of any solid depends uniquely, or its properties depend uniquely on the charge density. It may depend on something else. So There is recent progress towards extending the validity of these theorems to excited states, but all of the major issues that one sees from density functional theory in whatever formulation one prefers, they stem from this fact, which is the Hohenberg-Kohn theorem says that you can calculate only the ground state properties with the charge. It doesn't say that you cannot. It's not a necessarily insufficient condition, but it guarantees that the charge density is sufficient to compute the ground state properties. About the conduction band, excited states, you don't know. That's good, but what is dysfunctional now? So we have decided that we can re-express our single electron Schrödinger in quotes equation in this form: a kinetic energy of the electrons, a lattice potential, and this lattice potential is now the ionic potential plus the Hartree component. Okay, so I've lumped the Hartree here as well. So there is the ionic component, but then I have clearly the screening effect or shielding effects, whatever you prefer, of the core electrons. And you find in the conduction electrons also the valence electrons, so it's included here, the Hartree part, which is easy to calculate because I know how to calculate this term, right? It's just, I know the wave function somehow by iteration, so I can really solve Poisson equation and I'm done. So that's good. This is the tricky part, right? This is what we don't know. So at least now, thanks to the Kohn-Hohenberg theorem, we know that this is a function of the charge density. But what is it? I have no idea. So the usual approximation which is done, of course, but you know that there are improvements, is what Kohn and Sham proposed many years ago. In a crystal, the charge density doesn't vary terribly fast. It varies on the atomic scale, but kind of smoothly. So I know, thanks to what, for example, Gell-Mann and Bruckner did for the homogeneous electron gas, I know that the exchange and correlation functional, which is indeed a function only of the density, is a function of the, roughly, is the cubic root of the electron density. You realize this is, if I divide by 4 pi epsilon 0, this is exactly the energy of the Coulomb energy that I have, the average interaction between two particles. So I know what it is for the homogeneous electron gas. It's a constant, it's homogeneous. Let me assume that I can use the same form if rho changes slowly. So in here, I will plug kinetic energy, the lattice potential, the ionic potential, plus the Hartree component, and here I simply plug the cubic root of the local density, which is called local density approximation. Again, it's an approximation. The charge density varies slowly, but varies, so there may be corrections, and so there have been improvements. People have been looking for improvements to density functional theory since it came out the first time, some 50 years ago, because you're very well aware of the fact that, for example, if you calculate the band structure of many dielectrics, you get the wrong band gap. Not surprisingly, the valence band is fine. Actually, if you look at, particularly nowadays when you can relax the structure, so you can calculate the total energy as it changes as a function of the ionic positions, you can actually move the ions until they reach their equilibrium position, and you get extremely good agreement with with experimental data. For the conduction band is always an issue, and that's because it's an excited state. Okay, so people have said, well, first of all, let's look and improve the Kohn-Sham functional rather than consider only the local approximation. Let's consider the first generalization to the local approximation, which is, let's assume that the exchange and correlation function depends not only on the density here, but also on its gradient, which is the first non-local correction. Actually, it doesn't quite work if you just take any form which depends also on the gradient of rho. you violate particle number. So it has to be somehow generalized, a little bit ad hoc. You truncate an integral so that you conserve particle number. And it's called the GGA, the generalized gradient approximation. And now there are variations, the meta GGA and so on. Recently, there's been, in the past few decades, various hybrid functionals, as they're called, which actually give very good progress of the gap. The issue is that sometimes you don't get the higher conduction bands right compared to experimental data that probe like electroreflectance, optical absorption, that probe also the higher energies. There are variations which have gone now beyond the density functional, like the GW approximation, where G stands for Green's function and W for the screen interaction among electrons. So it's not an acronym here, it's just taking the symbols of the quantities which are of main interest. Nowadays, DFT has been used a lot to calculate electron-phonon interactions, so to calculate ab initio electron transport properties, such as the mobility. And there you see how this comes in haunt you, depending on what you do, what exchange and correlation function you use, if you use the GGA, if you use one form of GGA versus another, if you use what's called HSE, which is a particular implementation of the hybrid functionals, you get different numbers, different results, quite a bit sometimes. And the problem is that in many situations, transport properties are sensitive to energy errors of the order of KT, at room temperature, whatever is the temperature you're interested in. DFT is never accurate to 25, 30 millivolts. And unfortunately for transport, sometimes that matters a lot. And there are other issues that we may talk later on. Okay, I have about 10 more minutes. So any questions so far? I know that it is conceptually difficult. So if you want me to repeat, to explain something that I said, I'll be more than happy to do it. This is essentially the core of what we have to deal with in the first part of the class. Any question about this so far? Am I online? Still online? Can you hear me? Yes?
Yes, Prof. No questions so far.
No question. You understand everything. Good. I don't. This is extremely hard. Anyway.
I have to review the video.
It is hard. So please, if you look at it, if you read some more, if you have any questions, just shoot me an email or two, and I'll try and answer as best as I can. I'm not a DFT expert. I've struggled with using DFT to calculate electron-phonon matrix elements, and that is something that I'm still banging my head against. So I know a little bit about the pluses and minuses. What DFT is today is really amazing in terms of calculating the atomic structure. So it can really give you excellent agreement with experimental information about lattice constants, for example, or at interface relaxation effects, how the ions relax. This is really good. And valence band properties, the charge in the valence band, bonds, and so on. About the excited states, that's still an issue. I mentioned here something which is a dream, the holy grail, if you want, of what we're dealing now. Where's my laser? Here. There are, thanks to improvement in algorithms, for sure, and also hardware. Hardware computers are getting so much faster with, you can use tens of thousands of nodes nowadays and so on. So one can do things that were unthinkable before. So one idea is to do all electrons calculations. We will talk tomorrow about pseudopotentials. You can actually start doing calculations in which the lattice potential that I have here is really the potential of the nucleus. So if you're dealing with carbon, is a +6 charge nucleus, and then you have all the core electrons around it. So these are called all electrons calculations. they used to be unthinkable. We will deal again with, as I said, tomorrow with the pseudopotentials. The idea is, do you really need it? Do you care about what core electrons do when you're really interested in a conduction band or in a valence band or in bonds? Core electrons in silicon are 120 eV down. Who cares about them when you're dealing with a silicon-silicon bond and a crystal structure? Nevertheless, if you do that, you bypass this pseudoization issue, which is considered a model potential, which excludes the core electrons. And this has some advantages, because actually the choice of pseudopotential that you use, I'll tell you how you derive them from Hartree-Fock calculation on isolated ions. They're parameterized, and different parameterization can give you the same results for isolated atoms, but they will give you slightly different wave functions in a crystal. And that will affect the matrix elements, say, for the electron-phonon interaction. And when one can use GW, bypassing all these density functional approximations. Unfortunately, the exact form of these things is still undoable. Except in small molecules, there is a computer package called Gaussian that actually does a good job in this way, but it's limited to few tens, maybe 100 atoms. If you deal with complicated nanostructures, that DFT now is applied in cases to several hundreds of atoms, sometimes 1,000, and it keeps improving. So you always have a mix and match of a trade-off between the generality and the realism of the system that you are considering and the complication of the theory. The bigger the system, usually the more approximated and simpler the physics has to be. Otherwise, you cannot solve it. So let's step down to Earth here. Where are the bands coming from? I want to give you two approaches, two different arguments why you have band gaps. So why you have bands. One is very qualitative, which is what I will discuss it now in the next, how much time do I have? 5 minutes, then 5 minutes. And then we'll give a little more of a formal, next time or tomorrow, a little more formal argument of where gaps come from perturbation theory. So physically, what happens? Suppose that I have two silicon atoms very far away. Okay, they're all very far away. And we know how they are. The electronic structure, we have two electrons in the 1s core state, which is 1,000 eV down. There is the 2s and the 2p lines, which are the core states. These are about 125-ish electron volts down from the vacuum. Vacuum is somewhere here. And then we have the valence states. These are the outer shell. We have the 3s and the 3p orbitals. Clearly, we can put 6 electrons in a 6 orbitals, but we don't have them. We have only 4. So, 8 electrons in total. We have only 4. So we have 2 electrons in the 3s and 2 electrons in the 3p. Actually, the s and the p minimize their energy when you form a linear combination of them, and what's called a hybrid sp3 orbitals. And so you put 4 electrons into the sp3. 3 sp3 orbitals. So you have a bunch of states, in principle, all degenerate, all at the same energy. In principle, you could put 8 electrons in these states. You only have 4. So if you want, there is this set of 3 sp3 orbitals that contains half of the number of the electrons that it could contain. Okay, of course, same for the other silicon atoms, which is far away. So what happens if I bring them together now? An analogy that I give sometimes is if you have tuning forks, those that give you the A note. If you bang against the table a tuning fork, you hear the vibration, and that's fine. If you have 2 of them, and you bang 2 of them together, what you have is you hear beats. Despite the fact that the tuning forks are identical, their vibration interacts one with the other. So that actually the A note 400 and something hertz, it splits slightly because the vibration of one tuning fork are affected by the sound waves generated by the other and vice versa. And so you have that the two degenerate eigenfrequencies actually split slightly into two slightly separated frequencies. The same happens here. We bring these two silicon atoms together. In principle, we have 8 electrons, but remember that we have 8 possible states for each atoms. So we have 16 possible states that we have. But remember what we said, I think I have a slide here. What I said, how do you form a linear combination of those sp3 orbitals? Well, you can form bonding corresponding states by adding them in phase or by subtracting, so adding them out of phase in antibonding states. So what happens is that half of these states go into bonding states, and there will be 8 of them. We have 8 electrons, which are shared between the two silicon atoms. So what we have is a full set of 8 possible states, which are filled by the 8 electrons. And these are the bonding states, the bonding wave functions. And then we have the anti-bonding, which in principle will have a node here in between the two atoms. And they're empty because we don't have any electron. Okay. Now, this is what happens when I bring 2 silicon atoms together. We split these 2 states into 2. Okay. What if I bring 10 silicon atoms together? Well, then each of these will be split into 10 bonding states and 10 anti-bonding states. All of them separated slightly in frequencies, all of different energies, which is the same. All of the energy which is slightly separated, as if I brought into a room 10 tuning forks and I bang them against the wall all at the same time, and I will have a probably cacophony with lots of beats and of various combination, higher order beats. They all split into slightly different frequencies. And that's how I broaden each of these states into a band. Because if I have so many silicon atoms, 10 to the 22nd, 10 to the 33rd per cubic centimeter, what is the density? Something like 10 to the 22nd, right? Per cubic centimeter. I will have essentially a band, a continuum of possible states. So the bands are, and the gaps that I have between the bands are the result of the atomic orbitals that broaden and split into a quasi-continuum of states. And the energy gaps are just the remnants of the distance, the energetic separation between the eigenstates of an ion. I remind you that when we were talking about the Bloch theorem, I said that the wave function of an electron in a crystal is labeled by an index k and has the form of a plane wave, e to the I k dot r, times a u of k, and u is the periodic component, and that is a remnant of the orbital. So each of that u carries the same fingerprint of the particular atomic orbital where it was coming from, that it splits into a band, it broadens into a band. So next time, what we'll do is, just something that you know, but we'll talk about tomorrow. I want to go into a simple example of a band structure for a one-dimensional system, just to sketch where the bands are coming from this point of view of the chronic Penny model, and then give an idea about somewhere later on about where the energy gaps come from perturbation theory. And tomorrow we'll go also on into the subject of discussing pseudopotentials. I guess I can stop here because I'm running out of time. So any question again, please, once more, feel free to interrupt me, feel free to ask. It might be the fact that it's a different continent, different cultures, but I don't mind being interrupted, so please do. And if you don't want to ask me in class, send me email so we can have some interaction. So, no questions? All right, then have a good evening, I guess, and I'll see you tomorrow at 4. Thank you. Bye-bye.
you.